Well, how do you graph a logarithmic function? Well, let's look at example 9 here, graphing f of x equals log base 2 of x. Typically, we try to input something in here, but unless we really know anything about logs, we just don't know what's going on here. So I said earlier that logs and exponentials are inverses of each other. So the inverse of log base 2 of x is going to be 2 raised to the x power. Well, we already know points for this. Let's say we put in -2, -1, 0, 1, and 2. We've evaluated this in the previous video. This was a fourth, this was a half, this was 1, then 2 and 4. Right? If we're plugging in -2 in for x here, we'd get a fourth. -1 in for x, we'd get a half. 0 in for x, we'd get 1. 1 for x, we'd get 2. 2 for x, we'd get 4. The reason that we do this is, remember, these two functions are inverses of each other. So what do inverse functions do? They swap their x's and y's. So if these are the y's of 2 to the x, then those are the x's of log base 2 of x. So I'm going to write 1/4, 1/2, 1, 2, and 4 in the x position here for this functions table. And then these values that were the x's for 2 to the x will become the y's for my log base 2 of x. -2, -1, 0, 1, and 2. Remember, inverse functions swap that x and y. Well, let's put these points on here. So I have 1/4, -2, about here. Then I have 1/2, -1. I have 1, 0. I have 2, 1. And I have 4, 2. So if I'm graphing these so far, they look like this. I'm just going to aim it down, and I'm not going to touch my y-axis. Well, why wouldn't I touch my y-axis? Well, remember that 2 to the x, doesn't this thing have a horizontal asymptote at y equals 0? We figured that out when we were in exponential functions. Well, remember, everything changes for inverses. So instead of a horizontal asymptote, we're going to have a vertical asymptote. And instead of being y equals 0, it's going to be at x equals 0. So logarithmic functions will have vertical asymptotes at x equals 0. Well, what about the domain and range? Well, we can do this from the picture. If we look at this picture, the domain, well, the furthest left that I want to get to is this line 0. So it's 0, and then I'm going off to infinity. The range, bottom is an arrow, top is an arrow, so that's -infinity to +infinity. And if you think back to exponential functions, we reversed those two from exponential functions. Let's look at our picture. What about an x-intercept? Do I have one? Yes, I do. Here's my x-intercept. It's right there. That's the point 1, 0. Well, do I have a y-intercept? Do I cross this y-axis? No, I don't. I have none. Well, again, we swapped those from before with our exponentials, except for the point 0, 1 became 1, 0. Why? Because again, all of these things swap, the x's and the y's. Why? Because exponentials are inverses to logarithms. Well, let's look at some in generals here, and you'll notice that a lot of this sounds very familiar. So we figured out that if we have log base a of x, it's going to have that domain of 0 to infinity, and a range of all real numbers are -infinity to +infinity. Again, that's reverse from our exponential functions. We won't have a y-intercept, and our x-intercept, I'm sorry, this is wrong. Our x-intercept, please change that to say 1, 0. So please say 1, 0. Okay, our x-intercept is 1, 0. The vertical asymptote, notice this one's a vertical asymptote and not a horizontal asymptote. And this, I apologize, should say x equals 0. So make sure you update this to say x equals 0 and this to say 1, 0. So again, domain is 0 to infinity. The range is -infinity to +infinity. We don't have a y-intercept. Our x-intercept is 1, 0. Our vertical asymptote is x equals 0. And now, all logarithmic functions in that basic shape form, so no transformations, have two anchor points. What are those anchor points? 1, 0, and a1. For exponentials, what were our anchor points? Well, those were 0, 1, and 1a. If you look here, what did we do? we swapped the x and the y. That's what happens with logs and exponentials. You swap your x and your y. So when you're studying for these, really just think to yourself, okay, if I memorize exponentials, all I got to do is swap my x's and y's for my logs. Well, how do you graph these things by transformations? It's going to be exactly like we graphed by transformations for our exponential functions. What we do is we take those anchor points and we transform them depending on that horizontal shift and vertical shift and a reflection if we have it. Then we find our new vertical asymptote. What finds the vertical asymptote? The horizontal shift. Again, everything's changing, x's and y's. So the vertical asymptote here is found by that horizontal shift. Once you know where that vertical asymptote is going to be and where those anchor points are transformed to, you have the graph of your function. Let's take a look at graphing some of these. So we have to obtain the graphs of the following functions by translating, reflecting, and stretching. Give domain, range, and the equations of any asymptotes. Well, let's start with the first one. Log of x minus 2. The thing you're taking the log of is just x. It would be in parentheses like it is for example 11 over here if it was a horizontal shift. But it's not, so this is a vertical shift, and this is a vertical shift that tells me to go down 2 units. Well, I know I'm going down 2 units, so I don't have a horizontal shift, which means my vertical asymptote is going to stay at x equals 0. So I'm just going to go ahead and draw that in because that was really easy. Well, now I need my anchor points. My anchor points are going to be, remember, 1, 0, and then a, comma, 1. Well, what's a? Well, what's the base? Well, there's no base there. Well, what's the base when there is no base? When there is no base, that base is 10. So this is really 1, 0 for one point and 10, comma, 1 for the other point. We're going to change the scale here and have these all go by 2's just so I can get to 10 when we're graphing this. So 2, 4, this is 6, 8, 10. So I have the point 1, 0. So let's say 1, 0 is here. And this thing tells me, hey, move that down 2 units. 1, 2. So I'm only going to change the scaling of my x-axis, not my y-axis. So that's the new point. Well, what's that new point? That point becomes 1, comma, negative 2. Then I have the point 10, 1. 10, 1 was here, and it's got to move down 2 units because that's my vertical shift. Well, what's that new point become? Well, that new point becomes 10, comma, negative 1. So the 2 points is all I need to graph this. So put them together, and it aims down, and there we go. That's the graph of log of x minus 2. What's the domain of this? Well, the furthest left I want to get is 0, so it's 0 to arrow, positive infinity. And the range, bottom's an arrow, top's an arrow, so negative infinity to positive infinity. Let's look at example 11. Right, let's change this to have a log of 10 as well. So let's erase that little 2 there because all your classwork problems deal with log base 10. And if you're taking chemistry, you're going to be dealing a lot with log, which is log base 10. So let's just get used to log base 10 instead of the other ones. So we're just going to say this is 4 plus the log of x minus 1. So we erase that little base that was the base of 2. So we don't want that base anymore. We want to keep it as just log. So if there is no base, we know that our base is going to be 10. So what kind of shifts do I have? Well, this is in here in parentheses with your x. So this one's your horizontal shift. Well, horizontal shift, this one tells us I go right 1. Then there's this number out in front, 4 plus. Well, since it's 4 plus this thing, this one is my vertical shift, and that tells me, because 4 is positive, that I need to go up 4 units. So I have 4 plus the log of x minus 1. Right, what were my anchor points? The points on here would have been 1, 0, and then 10, 1. Did I have a horizontal shift? I did, so that means that I have a new vertical asymptote, and that's going to be at x equal, right 1, so x equal 1. So let's go ahead and draw that vertical asymptote. So I have the point 1, 0. 1, 0 would have been right here. What do I need to do to it? I need to move it 1 to the right and then up 4 units. Up 1, 2, 3, 4. So there's my new point. Well, what's that point? That looks like it's 2, 4. So that's the point 2, 4. Great. Now I need to transform the point 10, 1. Well, we forgot to change the scale, so that's okay. So we need to add some more axes here. So here's 1, 2, 3, 4, 5, 6. Let's call this 7, 8, 9, 10. So we're just going to move the axis a little bit this way so that we can graph our points here. So the point 10, 1, so 7, 8, 9, 10, 1 would be right here. And what am I supposed to do with this point? I need to move it 1 to the right there, and then up 4. So up 1, 2, 3, 4. So the new point would be right there. Well, what is that point? Well, let's see. That point, moving 1 to the right, made that, 11? So I'm 11, and then up 1, 2, 3, 4, 5. So this becomes the point 11, 5. So those are the 2 points. Now I just need to connect them and draw the graph. And when you have a base of 10, you will have this kind of oddly shaped graph. It doesn't curve very well, but that's okay. It's okay to have it look like a sideways L. What is the domain of this? Well, the furthest left I want to go is 1. The furthest right, arrow, so positive infinity. What's the range? Bottom part is an arrow. Top one is an arrow, so negative infinity to positive infinity. Okay, let's look at example 12. I have the natural log of x plus 2 minus 1. Well, let's figure out the base real quick. What's the base? Well, I have natural log. When I have a natural log, remember your base is e. So that means if you're thinking about the anchor points already, if the anchor points are 1, 0, and then a, 1, well, this a, my base is going to be e, so we can just write that as 2.7, 1. Let's figure out our shifts here. Well, this number is inside here with x, so this makes it a horizontal shift. Horizontal shifts are opposite what they say there. A plus 2 moves me left 2 units. Well, remember, horizontal shifts determine my new vertical asymptote, so my vertical asymptote is x equal negative 2. Let's go ahead and just draw my vertical asymptote of x equal negative 2 in here. Then I have that minus 1. Well, what is this minus 1? Well, that's a vertical shift, and that tells me that I need to go down 1 unit. So I'm going left 2 and down 1. So start with that point, 1, 0, which is right here. It needs to go left 2 units and down 1. So where does it become? It becomes the point, let's see, that's negative 1, negative 1. So my first point for this graph is negative 1, negative 1. Next point, the point 2.71. Well, here is 2.71 right about here. What is it supposed to do? It's supposed to go left 2 units. So here's left 1, there's left 2, and then I need to go down 1 unit. So right about there. So this point, well, what's that point? Well, if I were to be subtracting 2 from 2.7, this actually leaves me with a point 0.7, 1. So it's a point 0.7, 1. All I need to do is connect the points and draw my graph. There we go. What's the domain and what is the range? Domain, furthest left I want to go is this vertical asymptote of negative 2. So it's a negative 2 to positive infinity. My range, bottom's an arrow, top's an arrow. So negative infinity to positive infinity. All right, let's look at our very last one. I have 2 minus the natural log of x plus 1. Again, natural log means my base is e, so I know my points, my anchor points are 1, 0, and 2.7, 1. Right, let's figure out everything that's going on. Well, I have a minus. Well, this minus actually in front of the natural log is a reflection. So remember, reflections you have to do before you do anything else. So we have a reflection. Then we also have a 2 out in front. Since it's positive, it's a vertical shift, and that vertical shift tells me to go up 2. And then I have a number in here with x. My numbers with x are always determining my horizontal shifts. It's opposite what that says, so I need to go left 1. So I have a vertical shift of up 2 and a horizontal shift of left 1. Remember, your horizontal shift determines your new vertical asymptote, so this is going to be at x equals left 1 makes it negative 1. Let's go ahead and draw in that vertical asymptote before we do anything else. Right, so I have the point 1, 0. Here's the point 1, 0. I need to reflect it on the other side of the x-axis. Well, I'm on the axis, so I can't reflect myself. So now all I need to do is do my shifts. It says go left 1 and then go up 2. So this becomes the point 0, 2. So there's my first point. One more point is all I need to finish this graph. So it was the point 2.7, 1. So 1, 2.7, 1. Well, I need to reflect it on the other side of the x-axis. It's going to go right there and be 2.7, negative 1. Then I need to go left 1, so left 1 unit, and then I need to go up 2 units. So here's up 1, there's up 2. It's going to go right here. So what is that point? Well, that looks like it's 1.7, positive 1. So it became the point 1.7, comma, positive 1. So there are my 2 points. Let me erase all that. All I need to do is connect them. Now this graph, watch how it goes like this. And you might ask yourself, why am I not looking like this graph over here? Remember, in order to be reflected, and I'm going to draw something on the graph on number 12 and then erase it, but in order to be reflected on the other side of the x-axis, what you need to do is look like a mirror image. You have to be able to fold at the x-axis and line them up. So a graph that's reflected for natural log or logs is always going to be kind of decreasing down this way. So there's my graph. What's the domain? The furthest left I want to go is -1, so -1 to positive infinity. And then my range, well, the bottom's an arrow and the top is an arrow, so I say -infinity to positive infinity. Well, that's it for logarithmic functions.